In this video, we're going to be looking at how to solve for a voltage when there's a capacitor in the circuit using the step method. The first thing that we want to do is we want to find the voltage over the capacitor at time is equal to 0 minus. This little minus sign up here indicates that it is right before the switch is switched and that this circuit has been stable for a very long time. So I'm just going to redraw it on the next page with the switch completely open. Okay, so I've redrawn the circuit with the switch open. Notice that I've also made the capacitor open. That's because before the switch is switched, I've had this this voltage source right here, the 12 volts, connected for a very long time, and thus the capacitor is going to act like an open source. So what we can do now is we want to find VC, which is going to be the voltage over that capacitor there. So what I'm going to do is I'm going to do loop analysis inside both of these loops. There might be an easier way to do it. I'm just going to do it this way for now. Since this VC isn't open right there, we can make that whole thing one giant loop. So this is going to be the current I2, and this is going to be I1. So we have, going around the first loop, we have I1, and then we're going to put all the resistors in that I1. So we have the 12 plus the 6 plus the 3 plus the 6. And then minus everything that is touching the other loop. So we have this 3 and this 6 down here. So we're going to have minus I2, the 3 plus the 6. And that is going to be equal to 0. Now we're going to go ahead and go around the other loop. So we have I2, and then I have all the resistors in I2. So I have a 3, a 6, and a 3. And then we are going to subtract away everything that's touching the other loop, so minus I1, and then the 3 plus the 6. And then we'll go around this loop here. We're going to hit the negative sign on this voltage source, so we're going to have minus 12. And this is also going to be equal to 0. So what we're going to do now is we're going to just solve for these. You can plug these in MATLAB quite easily and solve for them that way. I've already gone ahead and done that. So we have I1 is equal to 4 over 9. We have I2 is equal to 4 over 3. Now that I have the currents, what I want to find is I want to find this VC. So I'm going to go ahead and I'm going to go around this second loop another time. But this time I'm going to act like this VC here is actually something in the way. So I'm going to go around it like this. So I'm going to say that I have I2 times the resistor 3, and then I have that plus on the VC, so plus VC, so we're just going to treat that just like a source, and then we have that minus 12, that was I2, and then we're going to have the resistors that it's touching, so that's going to be I1 times the 3. Notice how we just kind of sectioned this off and acted like this was its own little area over here. We also could have done the same thing using just this side of that. So now that we know I2 and I1, we can go ahead and plug those in and we will solve for VC. So we get VC is equal to 9.33 when we go ahead and plug those in. So now we know the voltage over the capacitor at time is equal to 0 minus, which is right before the switch is switched. So what we're going to do now for the step method is we're actually going to go ahead and we're going to go back to that original equation. We're going to switch the switch and then we're going to replace the capacitor with this voltage that we just found. So we're on step number 2 now. Let me just go to a new page for that one. So for step 2, we are replacing the capacitor with the voltage that we found. And we're also switching the switch. So I'm just going to go ahead and redraw this now. So what I've done is I've redrawn it with the switch. Now what I'm going to do is I'm going to replace this capacitor here with the with the voltage that we just found. And we want to make sure that we have it labeled the same way, positive and negative, that it was whenever we found it. So notice here that our VC was positive on top, negative on bottom. So we have a positive and then a negative, and that voltage was 9.33. So what we're going to do now is we're going to solve for the VO, or whatever we're trying to solve for at this point. We're going to solve for it with this capacitor replaced and with the switch switched. So let's do that now. I'm going to use nodal, actually not nodal, I'm going to use loop analysis again. So I'm going to call this I1 and then make this I2. Notice that we don't really need this one over here or this one right here because there's no resistors connecting these ones right here. So they really don't play a part in each other's equations. So we're just going to go ahead and solve for that now. So we have the I1 and then all the resistors in there. So we have 12 plus 6, which is going to be 18, minus everything that is touching, which is I2 resistor 6. And that is going to be equal to 0. And then we move on to I2. So we're going to have I2 times all the resistors that it's touching, which is a 6 and a 3, so that's going to be 9, minus everything that's touching the other loops. So that's going to be I1 times the 6. And then we go around this way and we're going to have the negative side of that voltage. So we're going to have a negative 9.33. And that's going to be equal to 0. So when we go ahead and solve these, we're going to get I1 is equal to 0.44. We don't really need that one, so we don't really have to solve for it. And we have I2 is equal to 1.328. So now we can see that the voltage VO is actually the current I2 going through the resistor right here that I forgot to draw, the resistor of 3K. So what we do is we do 1.328 times that resistor, and we are going to get the voltage of 4.14. So let's switch back and see what the next step is going to be. So after we have, we've done step 3, we solved for what we wanted at time is equal to 0 plus, which is right after the switch is switched with the capacitor in the equation. Next we're going to move on to step 4, which is solve for VO at time is equal to infinity without the capacitor replaced. So just keep in mind that's without. So let me redraw that for you really quick. So at time is equal to infinity, the switch is going to be switched, and we actually still have this source connected, and this source has been connected for an infinite amount of time at this, once we switch the switch. So this capacitor is again going to act like an open circuit, so we can actually just delete these for now. And we're going to be solving for VO again. So we're solving for VO at time is equal to infinity, and the capacitor acts like an open. So what we're going to do now is we can just do loop analysis, but if you want, you can actually shrink all these down first, so that way we're not dealing with so many loops. So we have the 6 and 3 in parallel, and then we have the 6 and 12 in parallel. So that's going to be, we have 6 times 3, that's 18 over 9. So that is going to give us 2, and then we have 6 times 12 over 6 plus 12, which is going to be 18, so that is going to give us, it's going to give us 4. And then once we shrink these down, I'll draw it really quick for y'all. What we have is we have one like that, and then we have one like that. And then all this other good stuff down here, like this one, and then that one. So we can see that these resistors are actually in series. We don't want to combine this 3K down here because this is what we're trying to find the voltage over, so if we can combine it, then we can't really find the voltage over it. So we can combine these ones in series, so we do 2 plus 4, which is going to give us 6. So let me redraw this whole circuit for you. So now we have the super easy circuit of 12 volts down here, and then we have a 6 resistor up there, and then a 3K resistor down there, and we're just trying to find this VO. So we can do one giant loop on that and just find the current, and then we can multiply that current over the resistor 3 here to find that VO. So what we have is we have I times everything in that circle, which is going to be 9, 6 plus 3. And then we have the minus 12 from the source right here. Notice how when we go around this loop, we're going to hit the negative sign first. That's why we make it a negative 12. It's equal to 0. So our current is going to be 12 divided by 9, which is actually 12 divided by 9. That is 4 over 3, or 1.33. So now we're going to get that current, and we're going to multiply it by that resistor 3 to get the voltage. So we have 4 over 3 times 3, which is going to give us a voltage of 4 volts. So now we have VO at time is equal to infinity, and we found VO at time is equal to 0 plus on this one. So now what we need to do is we need to go back to our steps. So we need to solve for tau now, where tau is equal to the capacitor times the resistance. So we need to find the R Thevenin, or the Thevenized resistance, which means that we are going to short all sources, and we're going to open all currents. So we can do that right now. So we have the 6 right here, and then we have the 12 and the 3 and the 3. And this is going to be after the switch is switched. So find R Thevenin at time is equal to 0 plus. So after the switch has been switched. And then that voltage source is going to be a short. And then we have this one right here. And we want to find the R Thevenin as if we're looking in through the storage device, which is the capacitor in this point. So we're just going to go ahead and shrink down these resistors. So we have a 6 here, we have a 3, and then a 6, and a 12, and then a 3 right here. So we have 6 and 3 in parallel. That is going to be 2, like we found before. So we have a 2, and then we have the 6 and 12 in parallel. I think that was 4 last time. So we have the 4 there. Notice that we can't combine these ones because we have to have this capacitor here, so it kind of breaks them apart. So don't combine those. And then we have a 3 here. So we can go ahead and combine this 4 and the 3. So what we're actually going to have is we're going to have this 2 here. And then we have 7 over here, because 4 and 3 in a series is 7. So now when we look in through this, it's going to look like we have the 7 in parallel with the 2. So if we do 2 times 7 over 2 plus 7, which is going to be 9, we're going to have 14 over 9 as our R Thevenin. So now that we've found the R Thevenin, what we're going to do is we're going to multiply it by the capacitance in order to find tau, which is what we need for our equation for number 6. So I went ahead and multiplied that out. Notice we have the 10 to the 3 and the 10 to the negative 6 because our resistance is in kilo and our capacitance is in microfarads. So that's why we did that. Next, we're going to go ahead and we're going to solve for equation 6, which is VOT is equal to K1 plus K2 e to the negative t over tau. So keep in mind that the VO that we solved for originally at time infinity is actually equal to K1, so we can say that the VO at time infinity is equal to K. So what we did was we actually went and we plugged that in as K1 here, and then we solved for K2 given the initial conditions. At the initial condition, VO was equal to 4, so then we go ahead